We're going to pick up with Chapter 5.2, talking about reciprocal identities. Each one of the trig functions is a reciprocal of some other function. So if we have the sine of a particular angle theta, let's say that the sine of theta is 3/4, what that means is that its reciprocal is cosecant. So the cosecant of that same angle would then be 4/3. That's what it means by reciprocal identities. If you have a decimal, so let's suppose that cosine of some angle alpha is 0.62, then the secant, which is the reciprocal of cosine of that same angle, you would just calculate it as 1 divided by 0.62, which would give you approximately 1.613. That's what's meant by reciprocal identities. This next slide covers the signs of function values. Whenever an angle is in a specific quadrant, its trig functions will be either positive or negative all the time. I teach an acronym, all students take calculus. And the way that works, quadrant 1 is all, quadrant 2, students, quadrant 3, take, quadrant 4, calculus. So here's what they all stand for. A stands for all functions are positive, just like it says here. The S for students stands for sine. So in quadrant 2, sine is positive. Because sine is positive, cosecant has to be positive because cosecant is the reciprocal of sine. In quadrant 3, we've got our T for take. That stands for tangent. The tangent is positive in quadrant 3. Because tangent is positive, cotangent must be positive. All other trig functions are going to be negative. And then in quadrant 4, that C for calculus represents cosine, and its reciprocal secant, and secant is 1 over the cosine. So in quadrant 4, cosine is positive, secant is positive, the other 4 are going to be negative. The next thing that's important to understand are the ranges of our trig functions. Remember, the ranges are just the y values that are allowed within those functions. For sine and cosine, our range is from -1 to 1. So I'll write that out. From -1 to +1. If you put into your calculator the sine of an angle and you get something larger than 1 or smaller than -1, check the mode, because you might be in radian mode rather than in degree mode. But you should never have a sine or cosine of an angle that's outside of the values -1 to +1. It can be equal to those two, but it can't be larger than 1, it can't be smaller than -1. Tangent and cotangent can be anything. That's what this means. All real numbers. Tangent and cotangent from -infinity to infinity. That's pretty simple. The harder one to remember are secant and cosecant. They can be anything except from -1 to 1. So all numbers except from -1 to 1. But if you look at the notation here, it's got these brackets. Secant and cosecant can be -1 and 1. They just can't be the values in between. Whenever we talk about trig identities, we have to include the Pythagorean identities. Remember that with trig, we're dealing with right triangles, and the Pythagorean theorem is essential when discussing right triangles. So the first thing that we're going to do is we're going to start with the Pythagorean theorem. X squared plus y squared is equal to r squared. Now in algebra, we're allowed to multiply or divide every single term in an equation by the same value, and the equation doesn't change. So in this case, we'll divide by r squared. From here, what we can do is we can take this term, x squared over r squared, and we can make that x over r squared. The next term can be y over r squared. And then the final term, r squared over r squared, really is just 1. Well, we know from the beginning of the chapter that x divided by r is really the cosine of theta. So this becomes the cosine of theta squared. Y over r is sine of theta. So we get sine of theta squared is equal to 1. This is not the notation that we use. Mathematicians don't like to write as a lot of things, so we condense this a little bit. Also, this particular Pythagorean identity, we start with sine. So the way that we write this is sine squared of theta plus cosine squared of theta is equal to 1. And that is our first Pythagorean identity. Now if I start with that Pythagorean theorem, but this time I divide everything by x squared, I get 1 plus y over x is tangent and r over x is secant. So my next identity is 1 plus the tangent squared of theta is equal to the secant squared of theta. Finally, I can do the same thing, but this time divide by y squared. This gives me the cotangent squared of theta plus 1 is equal to the cosecant squared of theta. Here are those identities which are also in your notes. For all angles theta for which the function values are defined, meaning that if we're dealing with something that the function value isn't defined, for example, the tangent of 90 is undefined, so if we tried to put 90 degrees into this, it wouldn't work because tangent is undefined at 90. With quotient identities, what we're going to do is we're going to start by dividing sine and cosine. From here, we'll say we remember that the sine of theta is y over r, and the cosine of theta is x over r. We can do that thing that we learned a long time ago where we copy dot flop because we're dividing fractions, so I copy the numerator, y over r. Dot means you turn the division into multiplication. Flop means you take that denominator and you make it its reciprocal. These cancel and you end up with y over x. And we should remember that y over x is equal to the tangent of theta. We can do the exact same thing with the reciprocal. Start with cosine of theta over the sine of theta. We get x over r divided by y over r. So that gives us x over r times r over y. And we're left with x over y, which is the cotangent of theta. Here are your quotient identities, again for angles of theta where the denominator is not 0. So anything where cosine is 0, this won't work. Anywhere place where sine is 0, that one won't work. So we'll start with calculating the tangent given that we have the cotangent. Remember, tangent and cotangent are reciprocals of each other. So if the cotangent of theta is 4, then the tangent is simply 1/4. Similarly, if I'm trying to find the secant, given that I have cosine, by the way, please notice that this is not written correctly because we don't put square roots in the denominator. Also, we would write that in simplest radical form, but I'm going to excuse that for now. So if I know that the cosine is -2 over the square root of 20, then the secant is simply its reciprocal, negative square root of 20 over 2. I would reduce this because the square root of 20 in simplest radical form would be 2 square roots of 5 over 2, and those would cancel, and truthfully the more appropriate answer is negative square root of 5. But it's much easier to see I've just started with a fraction and taken its reciprocal. Here we're trying to figure out what quadrant or quadrants this angle might belong in. To start something like this, I might sketch my coordinate plane and write in all students take calculus. This says that tangent of theta is greater than 0. That means it's positive. Here it says that the cosecant is less than 0, so it's negative. So I look for the places where tangent is positive. Tangent is positive in quadrant 1 and quadrant 3. So in which of those two quadrants is cosecant going to be negative? It'll be here in quadrant 3. So that's our answer, quadrant 3. Taking a look at the next problem, all students take calculus. I need something where the sine is positive and the cosecant is also positive. Well, I know that sine is positive here in quadrant 2 and also in quadrant 1. Cosecant is the reciprocal of sine, which means that cosecant is positive in the same places where sine is positive. So for this, we can say that these are true for both quadrants 1 and quadrant 2. On these examples, we need to decide whether or not these things are possible. So we have to remember those ranges. The easiest one for me to remember is that sine always goes from -1 to +1. So when I look at this problem here, where cosine is -1.7, I know that this is not possible. Then I start thinking about tangent. Well, tangent and cotangent go from -infinity to +infinity. So for the first one here with cotangent, that one is possible. And then finally, when it comes to cosecant and secant, that's the inverses of sine and cosine. So secant and cosecant are not possible in the places where sine and cosine are possible. You can have a sine value that's equal to 0, which means you cannot have a cosecant equal to 0. This one's impossible. This last example is similar to something that I will put on an assessment. I'm asking you to find cotangent and cosecant, given that we know cosine is the negative 7/25, and we know that theta is in quadrant 2. So if we're thinking about the location of this angle, the cosecant is going to be a positive value, the cotangent will be negative. In order to do this, the first place that I would start is with the Pythagorean identity. Sine squared of theta plus cosine squared of theta is equal to 1. What I'll do is I will replace cosine squared of theta with my fraction, and I will square it. So this becomes sine squared of theta. Negative 7/25 squared will become 49/625. Now I can subtract 49/625 from both sides. Remember that 1 can be rewritten as 625/625. So really I can subtract 625 minus 49. This gives me sine squared of theta is equal to 576 over 625. Then I can take the square root of both sides. Now when I take the square root of a fraction, remember I'm taking the square root of the numerator divided by the square root of the denominator. The square root of 576 is 24, and the square root of 625 is 25. So now I have sine of theta. Not really asked for sine of theta, but I am asked for cosecant, which is the reciprocal. So I can say that the cosecant of theta is 25/24, and I know that it's positive. The last thing I need to do is calculate the cotangent. Remember that cotangent is equal to the cosine over the sine. Well, I know that the cosine is negative 7/25. The sine is 24/25. So I can rewrite that, negative 7/25 times 25/24, and I get that the cotangent of theta is negative 7/24. And again, looking at what I did in the beginning, I know that cotangent must be negative.